Oh, I did. I did. Yeah, I left it from it is a table with it. Actually, how much is the dependence on paper is that the lower numbers. If this one plus whatever you think of I think I can check it here.
Okay, good afternoon everyone. So some of you have this doubt regarding one of the questions in the sample quiz. Why is something like 7FC0 illegal, whereas 7AA is illegal? This is illegal as an immediate operand, whereas this is legal. 1FC0 is legal. Yeah, that was a question. The answer is, okay, let's look at the binary pattern corresponding to this. So this is 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0. Now, this one is 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. So why is this okay? Why is this not okay? The reason is, we should be able to write that immediate as an 8-bit value rotated right by an even amount. So here, what is the 8-bit value that I can use? This is an 8-bit value, and that 8-bit value is F5. Rotated left by 3 bits, which is rotated right by 29 bits. So now you see, you need a rotation which is by an amount 29, which is bad news because we can only rotate by an even amount. And why is there such a constraint? Because we have only 4 bits left. And using that 4 bits, you can represent only even numbers between 0 and 31, in fact 30. Right? So there is a constraint that the rotation amount should be even, which is not the case in this case. How about the second one? You can take this number, you can take this 8-bit value, which is 7F, and rotate it left by an amount which is 6, which is 7F rotated right by 26. Rotation of something left to the left by a number n is rotation right by 32 minus n. Okay, so that's why rotate left by 6 is rotate right by 26. And 26 happens to be an even number, which is good news. So what will be the ROT? The ROT 4-bit value that is encoded in the instruction, it will be corresponding to 13, okay, which is 1101. So the overall instruction, the last 12 bits will look like this. It will be 1101 here and 0111, 1111. So these will be the last 12 bits of the instruction. Whereas here, it's not possible at all because your rotation is by an odd number, which can't be accommodated. Okay, and that's why this doesn't work, this works. Okay, other than that, I guess most of you are okay with the sample questions that you have seen. So yeah, let's continue from where we left off in this chapter, which is to talk about multiplier, division units, and to deal with numbers having fractions. Okay, so this is where I had sort of mentioned this before we ended the session. A multiplier, this is what we call an array order based multiplier or a fully combinational multiplier, which as the name implies is nothing but a two-dimensional array of orders. Okay, so it looks very similar to your normal pen and paper multiplication, where you write down, then you essentially multiply this with this, you write it this way, then you multiply this with the one in the decimal we call it tens position, but in binary it's 2 raised to 1's position. Yeah, and that is this. And since we are multiplying it with a bit which is in the 2 raised to 1 position, we essentially write it with a shift left by 1 position. Yeah? And so on. And then just add it up. And this is exactly what this does. So here you see the least significant bit of your result is simply A0 and B0. So here you can see it's simply an AND gate. But for subsequent bit positions or subsequent results, you have to do addition, and that's why you have orders here. Like for example, for B1, it is A0 B1 or plus, not or, A0 B1 plus A1 B0. Okay, it's arithmetic addition, not a logical OR. Okay, and so on. And we saw that the number of orders, full orders that you need is roughly in the order of m into n if you are multiplying an n-bit number by an n-bit number. Okay, the actual number is slightly less than m into n, but it's of the order of m into n. And the delay is of the order of m plus n. Because you see, a change in A0 can come in through this path. So you see the number of full orders it will have to pass through. In fact, there are a few other paths as well. All of them will have the same delay actually. So if you could look at this way as well. But all of them you can see will have a total delay of 8. In general, the delay will be of the order of m plus n, full orders. Okay, look at how many orders will a change in LSB propagate through to potentially cause a change in MSB. I mean, a change in LSB of one of the inputs potentially cause a change in MSB of the result. Right? So it's of the order of m plus n. So this is the idea of array order based multiplier, which as I had mentioned is very resource intensive and can potentially cause quite a bit of delay. But it's not uncommon at all. It is actually there in a lot of hardware implementations. Now let us look at things sequentially. Look at how to do things sequentially. Generally, when you do computation sequentially, you will take more number of cycles, but you can do that generally with less amount of hardware. Okay, especially if you are looking at larger numbers. A sequential multiplier scales very well, whereas a combinational multiplier, well, you can see the number of adders required is going to increase at a square law, right, approximately. Whereas here, it's a somewhat linear increase in complexity with the number of bits. Now, the price we are paying is that it tends to be slow. You will require several clock cycles before you get your result, right? And in the most basic form, you might require 32 clock cycles to get the result of a 32-bit multiplication.
Now, to implement a sequential multiplier in ALU, then how would the architecture know that the 32 clock cycles have been finished before you bring in the next instruction?
Yeah. So his question is, let's say if you are having a sequential multiplication unit, okay, the next instruction should be delayed by 32 cycles, right? Because you will take 32 cycles for this to complete. So how do you go about doing that? Well, you will understand it a lot better after we look at the circuitry that accommodates pipelining, etc. But the basic idea is this, that you can just disable PC. Okay, so you can wait for the result to be available before the PC is allowed to change to the next one. So you simply remove or reassert the enable of PC to freeze PC so that the next instruction won't come in. That's a fundamental idea. Okay, now how do we do this multiplication? We assume that we have a 64-bit arithmetic and logic unit for a 32 by 32 multiplication, which kind of makes sense because if you do 32 by 32 bit multiplication, your result can be up to 64 bits. In general, if you multiply an n-bit number by an n-bit number, your result can be up to m plus n bits. Okay, which again makes sense if you think of what these m and n represents. Okay, it's kind of like logarithms, right? M-bit number can be up to just below 2 raised to n. N-bit number can be up to just below 2 raised to n. So when you multiply them together, the result can be up to 2 raised to m plus n or just below that. Okay, and that will require m plus n bits. That's the reason. You get it? Okay, what I meant is, if you have an n-bit number, it can be up to 2 raised to n minus 1. Okay, assuming that sign. N-bit number 2 raised to n minus 1. If you multiply them together, it can be up to 2 raised to m plus n minus a small value. Yeah? Which requires m plus n bits. And that's why if you multiply m-bit number by an n-bit number, you will require up to m plus n bits. Okay, think about what is the case for addition. What if you add an n-bit number with an n-bit number? How many bits will you need? Okay, think about it. We'll come back to that later. But here, okay, that's why we require a 64-bit ALU, and your product also requires a 64-bit register. Now, assume that your product register, okay, which at any point of time holds a partial product until the process is complete. And once the process is complete, you are looking at a full product, right? So this holds the partial product, and it is initialized to zeros. And here we are considering an example case where we multiply a 3-bit number by a 3-bit number. So your result can be up to 6 bits, and that's why we have a 6-bit register. And let's say the numbers we are looking at is 0, 1, 1, which is a multiplier. Sorry, multiplicand. 1, 0, 1, which is a multiplier. So we are multiplying A by B. So A is a multiplicand and B is a multiplier. Now, what we do is, we have B in a register, A also in a register. Originally, A and B are both 3 bits. Yeah? Or if you are looking at n-bit multiplication, both of them are n bits. But we require a 2n-bit register for A. Okay, and the reason will be apparent very soon. For B, an n-bit register is good enough. Your ALU has to be 2n-bit, your result can be up to 2n bits. So that's why we have 6 bits for S, and we will see for A also we have 6 bits, B 3 bits is good enough. Now, what we do first is to check the least significant bit of B. If the least significant bit of B is 1, it means A has to be added to the sum. You see here, what we do is, okay, we check this. If this is true, it means this needs to be added to the partial product. Okay, the current partial product. So we include it in our sum, sum of all the so-called partial products, right? So we include it, whereas if B0 is 0, then you essentially zero out these. And that's the beauty of binary, right? Multiplication by binary is either taking the original value itself or 0. So that's exactly what we do here. So here we are looking at the least significant bit, which happens to be 1. And since that least significant bit of the multiplier is 1, we add A, which is a multiplicand, to your partial product. Okay, the partial product so far, which is 0 plus A, the 6-bit version of A. So now our partial product becomes 0, 0, 0, 0, 1, 0, 1, 1, this one. Now we shift A to the left and B to the right. Why do we do that? Because we are done with this. Now we are done with dealing with this bit. This bit is no longer important. Now we are dealing with this bit. We are multiplying this bit with this. And since we are multiplying it with the 2 raised to 1 position, this effectively has to be shifted left by 1 position. And that's why we shift A to the left by 1 position. Okay, we are essentially doing A into B1, okay, which is A shifted left by 1 into B1. Okay, this is B1 in this position. So if B1 is taken into this position, we are doing this. Yeah. So we shift A to the left, B to the right. That completes the first step. Now it was originally 101. Now 0 comes in at the least significant bit position of B. So originally it was 101. After shifting, this 1 gets thrown out, and now our least significant bit is 0. So you are essentially doing 0 into the original A shifted left to the original A shifted to the left by 1 position. Okay, so that is 0, 1, 1, 0 into 0, which is 0. So we don't have to add A in this step. Okay, so we don't have to add A to S. Now you shift A to the left, B to the right. So basically in step 2, your partial product is not updated. S is not updated. Okay, because it was A shifted left to the A shifted to the left by 1 position into 0. So we don't add anything to S. And now after the second step, the 1 which was originally in the MSB position is now in the LSB position. And since it is 1, we have to add A to S. And A was shifted once here, shifted again here. So it's essentially here the original A shifted left by 2 positions. Which again kind of makes sense because now the B that we are looking at is the original B2, which is in the 2 raised to 2 position. And that's why A shifted left by 2 positions, which is essentially A into 4, A into 2 raised to 2. Okay, so that is added to S. And that essentially means the original S plus the original A shifted left by 2 position, which is this plus this, which is a correct result. And numerically, okay, for now, assume that everything is unsigned. It makes sense because you have 5 here, you have 3 here, 5 into 3, 15. All good, right? Yeah. So the idea is fairly straightforward. You keep shifting B to the right to take out bits 1 by 1. And if the bit taken out is a 0, you don't do anything to the partial product. If the bit taken out is a 1, then you add A shifted by an appropriate number of bits to the partial product. Okay, and that appropriate number of bits is the original position of the B bit that we are looking at right now. So in the third step, we are looking at B2, and that's why we are looking at A, the original A shifted left by 2 positions. Yeah, that's it. Quite straightforward, but rather inefficient as we put this. Okay, because we are doing 64-bit operations over and over, but you see, even though we are looking at 64 bits, most of those bits are not really active participants in the addition process. Okay, the real arithmetic happens only for some 32 bits in between. Okay, because you see, you are looking at shifted version of A, right? So it's only that A, which is originally 32 bits, that gets added. Okay, on either side, it's all zeros. So you end up doing 64-bit arithmetic, even though in reality, only 2 32-bit parts get added. And that's the idea of that's the idea that we exploit in an improved design, improved sequential multiplier. The idea here is that we don't shift A, we shift the sum instead. So instead of moving A to the left and adding, we keep A and move S to the right and keep adding. Okay, so it will still be correctly aligned as it is supposed to be in that particular step. We avoid shifting A altogether. Instead, shift S. Here shift S was not shifted, but A was shifted. Here A is not shifted, but S is shifted. Here A was shifted to the left, here S is shifted to the right. Okay, but in both cases the alignment will remain correct. So we can make use of a 32-bit ALU instead of 64-bit, because practically we will be looking at only a 32-bit alignment, right? So yeah, and we don't use a separate register to store B, because after n number of cycles, and here n is equal to 3, the original content of B is not interesting anymore. B is used simply to take bits out of it one by one and then decide whether A is supposed to be added or not. That was the only reason why we use B, right? So we just put B here in the right hand side of the S register as an initialization. So here it will be 101 on the right hand side. Okay, and on the left hand side you will have zeros. So that's why that S register will be initialized as zeros here and the original content of B on the right side. Okay, now we will do the same process with some differences. We look at the least significant bit of B, which appears here. So that goes into a control circuitry. Control circuitry will look at it and it sees that it is 1. And then it will add A to S. But A is added to the extreme left of S. That sounds a bit illogical, right? Or does it? No, it sounds logical when you think of the fact that S is actually going to be shifted to the right. Okay, so eventually the first bit that gets added will appear at the extreme right after all the shifts. Yeah, so it's okay. So S is added with A, which is left aligned. So A is added to the left side. And what you get is something like this. Of course, this part is original B itself, and this is now the added A. Now you shift S to the right, okay, which will simultaneously shift these bits as well as B to the right. And that will give you something like this. Something like this. So S is shifted to the right after the first step, so you get something like this. And you can see now in the next step we can look at B1, that is bit 1. Earlier we looked at B0, now we are looking at B1. and that is 0, so there is no addition required. So you can simply say S is equal to S plus 0, because A is not added, and then shift S to the right. So that will cause this to be something like this. So 2 bits of the original B are now thrown out. And we are looking at the third bit, which is B2, the most significant bit of B. And that happens to be 1. So we do S is equal to S plus the left aligned version of A. The alignment of A doesn't change through the whole process. And we get like this. Yeah? And now this is not the final result, because there is still that bit of B that needs to be thrown out, and S was shifted overall only 2 times so far, so it needs to be shifted a 3rd time now, and you will end up with this, which is a final result. Yep. Now a caveat or a disclaimer, it doesn't really, this algorithm that I demonstrated just now requires a slight tweaking to work in most circumstances. I will give you a hint, I will leave the rest for you to figure out, which is how to deal with carry. Yeah, here we did not see carry at all in the whole picture, right? So a slight modification needs to be done in cases where there is a potential carry. Okay, think about it, but to understand this idea of what's going on or how it can be optimized, this is good enough. Now let us look at division, which I will not go through in that great detail. Division is in fact mostly a homework exercise for you, which is the main part of your lab 3. Yeah. So in lab 3 you have to understand division, you have to implement division, and hopefully even try a bit of optimization. Again, the basic idea is not particularly difficult. It is somewhat similar to your pen and paper method. So how do you do division? First you subtract in a left aligned manner, subtract the divisor from the dividend, right, on the left, and then we gradually move to the right. That's how we do pen and paper division, right? So even in hardware, the idea is very much the same, an algorithm. Okay, so this is what we call the so-called long division. We see whether it can be subtracted, then set the quotient, and then we bring down the next digit. Okay, see whether this can be subtracted from this. So at each time, in pen and paper multiplication, you are seeing how many times it can be subtracted, and that is what becomes your quotient. Here in binary, that how many times does not really make sense, because it's either possible or not possible, right? Because now how many times does not arise. So is 100, or can 100 be subtracted from 10? You can't. Okay, so you put 0 here, and then you bring down the next digit. So 101, can 100 be subtracted from 101? Not really. So you put a 0 here, and you bring down the next digit. Now it is 1010. Okay, can 100 be subtracted from 1010? Yes. So you put the quotient to 1. Okay, and you get your remainder 10. So it's the same idea as long division, except that in long division, like for example, if I am dividing 87 divided by 3, what I essentially do is I will see how many times 3 can be subtracted from 8, and I can do it 2 times, right? And that's why I write 6 here, and then you have 2, 7, and so on, right? So that's the idea. Now, okay, now it's the same idea here, except that, like I mentioned, how many times does not really occur or does not really make sense here. It's a question of whether it can be subtracted or not. Yeah? That's it. So it's the exact same idea that we follow in division hardware. This is the division equivalent of the original, non-efficient multiplication. Not the most efficient scheme, but easier to understand. Now it will be it will be a bit easier if you look at this example. So here we have an example where 011 is divided by 0010. Okay, before you do division of an n-bit number by an n-bit number, you convert the dividend into 2n. Okay, and here we are assuming, okay, here signed or unsigned doesn't really matter, you put zeros in. Okay, but things could be tricky if this bit is 1 and if the number is supposed to be signed. Then you have to do sign extension, otherwise you have to do 0 extension. So division operation is not the same for signed and unsigned. Okay, even multiplication has its problems, which I will see later. Okay, anyway, here there is no ambiguity at all whether it is signed or unsigned. It's going to be zeros anyway because the number is positive. Okay, so this is your original number, which is dividend. This is divisor. Now you started with subtracting the divisor on the extreme left, not on the extreme right, right? So same idea here. Even though the divisor is 0010, we make it 0010 0000 so that it is left aligned. And then you do the subtraction. So it's essentially dividend minus divisor. And we mentioned it remainder because at some point when the subtraction really happens, we don't really have the dividend anymore. Then all we are left with is the remainder at that point. That's why it is titled remainder, not divisor. Yeah? But for now, at least in the initial step, remainder is the same as divisor. Sorry. Okay. Remainder is the same as dividend. Okay, so this is originally dividend. You keep subtracting divisor from the dividend, and each time you get a remainder. So then you don't have dividend anymore. In subsequent steps, all you have is remainder. Sorry. It's dividend here. So original dividend is here. Divisor is this. So divisor is subtracted from dividend, and you get a negative number. And that makes sense because, well, if you do 0 0 0 0 0 0 0 0 0 1 1 minus 0 0 1 0, it is left aligned. And then when you do the subtraction, it's negative here. Yeah. So since it is 1, it starts with MSB 1, the result is negative. So what you need to do is, you need to add back the divisor to the current remainder to get back the original remainder, or in this case, the original dividend. Because nothing has been subtracted permanently yet. And then you set your quotient to 0. Your quotient bit is set to 0. More significant bit is 0. And then you try again after shifting your divisor to the right. So here you see what you do is you keep shifting this value right and subtracting. You keep shifting to the right and subtracting. So that's what we do here. You shift the divisor to the right and subtract it from the current remainder, which is still the current dividend because nothing has been subtracted away yet. You can allow something to be subtracted away permanently only when quotient is 1. And so far quotient is 0, right? Only when a quotient bit is 1, that subtraction is allowed to stay. Whenever quotient is 0, you don't allow the subtraction to stay, so you undo the subtraction. And undoing the subtraction is essentially adding back what you subtracted from the current remainder, which is essentially adding divisor back to the current remainder. That's the idea. So here again, you can't subtract. So basically you subtract and get negative. So you restore this by adding this and this. So your divisor is added to the remainder to get the original remainder. And you set the quotient, next quotient bit to 0. Okay, and keep doing it. And this time also you can't. You subtract the divisor shifted right by one position. Again 0, no luck. So you have to do a restoration. So you add back the divisor to the remainder to get the original remainder. Set the quotient bit again to 0. Yeah, and then shift the divisor to the right again and do the subtraction from the remainder, and this time you get positive. So remainder is positive, which means that subtraction was successful. And then you set the quotient bit. Okay, and then you don't restore your remainder because subtraction was successful, quotient bit is set, so there is no need to restore. Okay, and then shift remainder, so divisor to the right, subtract it from the remainder. So remainder was 0, 0, 1, 1. You subtract the divisor, shifted version of divisor, which is 0, 0, 1, 0. And this time also the subtraction is successful. So one more bit of the question. Okay. After you proceed from one step to the next, the potential quotient position or bit position is going to the right. So now the least significant bit of the quotient is set. Okay, and then your eventual remainder is this. And now there is no question of subtraction anymore. So what you are left with is essentially your remainder. So the idea is this. Okay, you align your divisor to the extreme left of the dividend. Do the subtraction. If it is successful, set the quotient, and what you get is a remainder from which you do further subtraction. If it is not successful, you add the divisor back to the remainder to get the original remainder. And set the quotient get to 0. Okay, and proceed until the divisor is right aligned. And then we see. So how many steps will it involve? If you are writing it in a sort of a loop, how many times will you need to do? It's actually n plus 1. Because this is dividend, this is divisor. First you start with extreme left aligned and go all the way until it is extremely right aligned. So the total number of steps is actually n plus 1. Yeah, you can verify it. Easy to see. So this requires n plus 1 steps. But that doesn't mean n plus 1 clock cycles. Why is it not the case? Or why do I say n plus 1 steps, not necessarily n plus 1 clock cycles? Because in each step, the number of operations that you have to actually do could vary depending on whether that subtraction was successful or not. If the subtraction was not successful, you have to restore, which is an additional operation. Okay, so if you implement it directly in hardware, the number of clock cycles required is actually variable. It's greater than or equal to n plus 1. Yeah, but variable. So you can see that there are a couple of issues. Number one is the variability, which might or might not be okay depending on your hardware design. The variability in the number of cycles required. The second issue is that, well, you can get an intuitive feeling that things don't really look very efficient, right? You know, restoring, etc. So indeed, there are more efficient schemes available, like for example, non-restoring division. You will realize if you read through non-restoring division algorithm that the whole restoration process is in fact unnecessary. Okay, it's mathematically a bit challenging to figure out why it is so, but yeah, go through the algorithm. I'm sure as third year electrical or computer engineering students you can just go through the YouTube Wikipedia article and you can sort of get an idea that you can avoid this whole restoration and allow division to complete in a finite number of cycles. And that algorithm is called non-disturbing division. Okay? Again, pop-up exercise is now, typically in a low-end processor, you will be doing only a multiplication or a division, not at the same time. Okay? Especially for a single issue processor, where at most one instruction is freshly issued, you wouldn't be doing a multiplication and division at the same time. Whereas you can see the hardware required for that, the infrastructure required for that looks quite similar, right? So actually, yes, it's possible to design a unit which shares most of the hardware for multiplication and division. Okay, which is not the case with high-end processors, which have several multiplication and division units anyway. Okay, there is no attempt at all to share it. Sort of us, again, depends on the exact design. Now, let us look at the issue of sign. For addition and subtraction, the hardware that performs them is exactly the same for signed and unsigned. There is no signed order versus unsigned order because it's the exact same operation, exact same hardware. Which is not the case for multiplication and division. And you will see why if you simply look at this example. I am doing 1 1 into 1 0. Okay. 1 1 into 0, all zeros. 1 1 into 0, it's 1 1 shifted to the left by 1 position. Add them up, you get 0 1 1 0. And here it was n bit, the result is 2n bit, so that also kind of makes sense. How about the interpretation? Unsigned interpretation is that it is 3 into 2 and the result is 6, which is very good, which is what is expected, right? But when you look at signed interpretation, you will see there is a problem. What is 1 1 signed? 2-bit signed? It's -1. Okay, look for the first one from the right, complement everything to the left. So your magnitude is 1, sign is negative, -1. The second number, 1 0, is -2. Right? Look for the first one from the right, write down everything, complement everything to the left. There is nothing left in the left to complement, so nothing. So the number itself is its magnitude, so -2. So -1 into -2 is, well, +6. You can say things are not very good, right? So what is the mistake that we did? Putting zeros in front is okay for unsigned numbers, but is not okay for signed numbers, especially negative numbers. Putting zeros in front can change the meaning altogether, right? Even the sign is changed. The entire meaning is changed. So putting zeros in front and doing it the way we did so far has its problems. So how do you fix the problem? Instead of doing zero extension, do sign extension. That's it. And it's easy to understand when you do sign extension for the full, 2 numbers. So multiplier. It was 1 1 into 1 0. Change it to 4-bit versions because you are expecting your result to be 4 bits, right? So change the operands to 4 bits first, and that will cause it to be 1 1 here and 1 1 here because both are negative. So sign extension will cause ones to be introduced rather than zeros. Okay, and then you do your normal multiplication the normal way, and you get 0 0 1, which is correct because -1 into -2 is supposed to be +2. All good. Now, an interesting point to note here is, well, there is this MUL instruction, right? Will you specify whether we are doing signed or unsigned? In MUL, you did MUL R1, R2, R3. You did not specify whether it is signed or unsigned. Was that okay? Because now I am saying that signed and unsigned are not the same. The operation is very different. Well, the point to note here is that when you do two n bit multiplication, that is n bit by n bit multiplication. And if your result is within n bits, your result is the same. So here it was unsigned, here it is signed. If your result fits within n bits, the operation is exactly the same. The result is exactly the same. Signed versus unsigned matter only when you are trying to get a 2n bit result. When you multiply 2n bit numbers. Okay, so if you are dealing with small enough numbers that the number comfortably fits, or the result comfortably fits into n bits, the result is correct whether it is signed or unsigned. The result becomes different only when you want a wide multiplication. That is, if you want full 2n bit result. Yeah. Now, this phenomenon doesn't really apply to division. For division, signed versus unsigned always matter. Okay, irrespective of what is the size of operand, we have to do things differently for division. Now, there is an easy way to do this multiplication and division, signed and unsigned, signed multiplication and signed division using unsigned. So let's say if you have two numbers, A and B, which are signed, find their magnitudes. So if A and B are signed numbers, and if you are doing, let's say, multiplication, multiply the magnitude of A with the magnitude of B. And if the two operands have the same result, don't do anything with the sign, because it will be positive. Negative into negative, or positive into positive will be positive. Whereas, if they disagree in their sign, negate the result that you get. Negation essentially is 2's complement, right? So find the 2's complement of magnitude of A into magnitude of B, if A and B have different signs. Same thing for division. Okay, find the magnitude of A divided by the magnitude of B in an unsigned manner, even if A and B are signed. And if A and B have the same sign, your result has a correct sign already. If A and B differ in their signs, just negate the sign of the result. Oh, sorry, negate the result, which is do the 2's complement of the result. That's it. By the way, there are several multiplication algorithms out there. You can read up if you are interested. And these kind of stuff like multiplication and division are still things which people try to improve and enhance. Okay, it's not a closed chapter yet. So even when you look at recent papers, there are actually people coming up with algorithms and schemes for more efficient multiplication, division, etc. Yeah? You can read up if you are interested about something called boot algorithm, which is very popular for side multiplication. Okay, so that completes multiplication and division. You will be doing that hands-on in lab 3. Now let us look at numbers with fractions. So far everything was integer, right? We are dealing with things which are integers, which means there is nothing after the point. Decimal point or binary point or whatever. Okay? Nothing after the point. Whereas if you are dealing with numbers where there are significant digits after the point, the representation systems that we have seen so far, which is whether it is signed integer, unsigned integer, isn't good enough anymore. And then we have to improvise and come up with some representation systems which allow for fractions. And there are two of them in practice, fixed point and floating point. Now, one popular misconception that a lot of people have is the moment they see a point, they use the term floating point, okay, which is incorrect. Okay, floating point is one possible way where you can represent numbers with fractions, not the only way. There is fixed point, which is actually getting more and more popular these days. the binary point is implied. So let's say we'll see with an example 6.75, and let's say the representation system that we are using has 4 integer bits, 4 fractional bits. So sometimes we call it a 4.4 format, where there are 4 digits before the point, 4 digits after the point. Again, don't always call it a decimal point, it's just called a radix point. So it depends on what your radix is. If you are using decimal number system, you call it a decimal point. If it is binary, you call it a binary point. Now, unfortunately, the notations are not so standard. You can find a lot of different notations for fixed point. Okay, some people write it as 4.4, some people write it as 8,4, where there are a total of 8 bits available, of which 4 bits are used for integer part, which naturally implies that the other 4 bits are used for the fractional part. Okay, so this kind of a format is used by companies such as Texas Instruments, which is famous for their digital signal processors. There are some other companies like Xilinx, they use this notation. So that's why how many bits are allocated for the integer part and how many are for fractional part is not having any standard notation. Okay, some people even use the other way around. Total number of bits, and this is the fractional bits, not integer bit. So it can get quite confusing. But these two are fairly popular ways of representing. And then again comes the confusion on what if it is signed. Is the signed bit counted in the number of bits here or not? Again, nothing standard about it. But yeah, for now, we have 4 integer bits, 4 fractional bits. So using those 4 integer bits, you represent the integer part, which is 6. Using the 4 fractional bits, you represent the fractional part, which is 0.75. 0.75 decimal is 0.11 binary. Why is it so? This is 2 raised to minus 1, this is 2 raised to minus 2. So it's essentially 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2, which is 0.5 plus 0.25, which is 0.75. Yeah? Yeah, the meaning is already given here. 2 raised to 2, 1 into 2 raised to 2, 1 into 2 raised to 1, 0 into 2 raised to 0, then 1 into 2 raised to minus 1, and so on. So we don't have to represent this explicitly. There is no mechanism to represent the position of the point explicitly. It is implicit. So the party who is writing it and the party who is reading it has to be in agreement regarding where the point is supposed to go. And here, if we follow that 4.4 format, let's say if there is one block A and there is another block B, where the output from A goes to B. Yeah? So block A and block B are both designed in such a way that the position of the point is implicitly in the middle. It's agreed upon beforehand. Yeah, and that's why, well, it works. Once A gives the information, B is able to figure out that yes, it is supposed to be the equivalent of 6.75. Now, it can be signed 2, and here again you can do 2's complement or sign and magnitude, etc. So let's use 2's complement, minus 7.510. Here again, 4 integer, 4 fractional bits, and we assume that the sign bit is essentially a part of your integer part. So you have the original number, which is for the magnitude in 8 bits, or plus 7.5. So plus 7.5 will be represented this way. Okay, 7 will be using 4 bits, 0.5 using 100. But we are looking at 510, right? Why did I not talk about this 0.1, 0.01? I am representing plus 7.5. The reason is, the error here is 0.01. 0.01 is too small a fraction to be represented using 4 bits. Using 4 bits, the smallest precision you can get this 1 by 2 raised to 4, which is 1 by 16. Anything less than 1 by 16, which is the case with 0.01, will have to be thrown out. Yeah? Of course, there are some rules regarding how to throw it out, which are called rounding modes, which we will see later. Yeah? But here, the so-called rounding mode that we use is truncation. Okay, whatever that can be represented is simply mercilessly thrown away. Now, this is plus 7.5. Invert bits and add 1, which is how you do 2's complement, right? And this is what you get. So this is a 2's complement representation of minus 7.5. In a representation where you have 4 integer bits and 4 fractional bits. Now, addition operation and subtraction operation are exactly the same as their integer equivalents in this representation. You don't have to do anything additional to do addition and subtraction. It's the exact same operation. Exact same thing. But when it comes to multiplication and division, there is a small problem. What is the small problem here? See, when we have when we have 4 fractional bits and 4 integer bits, 4 integer and 4 fractional bits. So for example, if you are looking at something like 100, 1000, there is an implicit point here. But remember, that point is implicit, it's not explicitly mentioned anywhere. So the actual representation is the original number into 2 raised to 4. So the original number was supposed to be this, right? Into 2 raised to 4 is what you represent. So there is an implicit scale factor of 2 raised to 4. Now let's say if I have a number A, I have a number B, okay, which are all or which are both having 4 integer bits, 4 fractional bits with an implicit point. The actual representation doesn't have the point. So the actual representation is, let's say, A, which is A into 2 raised to 4, small a into 2 raised to 4. Because that point is not represented. And the moment you take away that point, you are essentially multiplying by 2 raised to 4. Or shifting the point to the right by 4 positions. Or shifting the number to the left by 4 positions. Okay, which is multiplication by 2 raised to 4. Here B is B into 2 raised to 4 and the eventual representation is as A and B. Now let's do the multiplication. The multiplication is done using a standard integer multiplier. Okay, and what you get is A into B, which is nothing but A into B into 2 raised to 4 into 2 raised to 4. You see the problem? That scale factor got multiplied 2 times. What you expect, let's say if the original result is supposed to be C, its corresponding representation is supposed to be C into 2 raised to 4. But now what we are getting is essentially C into 2 raised to 4 into 2 raised to 4. You see the problem? So how do you fix it? Whenever there is a multiplication, you divide it by 2 raised to 4. Or in other words, you divide it by 2 raised to the number of bits used for the fractional part, which in this case is 4. You see the problem, or you see the solution? So because 2 raised to 4 got multiplied 2 times, you have to remove one of them so that you will have your result C, which is the small c into 2 raised to 4. So to bring it back to the original representation system, you have to scale it by 2 raised to 4. And of course you won't do division when the division is done with a divisor which is 2 raised to something, right? You simply do shift. So dividing by 2 raised to 4 is nothing but shifting left or shifting right. Yeah, shifting right by 4 positions. Shifting the number right by 4 positions. or shifting the point left by 4 positions. It's the same thing, right? Shifting a number to the right is shifting the point to the left. So you have to shift 4 points to the left, or shift 4 points to the left, which is shift the number right by 4 positions. That's right. Okay, I have just clarified it as a separate note. I will update the slide and give it to you, because in the original pricing there is an ambiguity on what you are shifting. If you are shifting the point, you shift it left. If you are shifting the number, you are shifting it right. Okay, which is a fairly simple operation. So luckily enough, even though we are dealing with numbers with fractions, there is only one additional step which doesn't seem to be that complicated. Yeah. Now, how about division? Now, same story. Let's say if I have A, I represented that it as A into 2 raised to 4. Let's say capital A. I have a number B, which is represented as capital B. Okay, when I do A by B, because A is eventually how it is in memory, capital A. Capital B is how small b is represented in memory or registers or hardware. So when the hardware does the division, it's doing A by B, which is what it sees, right? And the result is that you get a small c when what you expect is a small c into 2 raised to 4, which is capital C. This is what you expect, this is what you get. So how do you fix it? You ended up removing the scale factor. So you have to reintroduce the scale factor, right? So you have to do the division and then multiply it with 2 raised to 4, which is done by shifting the number left by 4 positions or shifting the point right by 4 positions. It's the same thing. Yep. Now it is quite popular, especially with custom hardware designers, and gaining quite a bit of popularity because it's a lot simpler than floating point operations to do. Yeah. So now let us look at floating point, but I guess it's a good time for us to pause. You can take about 10 minutes to run to the washroom if you want to, and be back here by 7:15. But before you go, let me just mention some ground rules. Okay, wherever possible. Okay, I am not having a seating plan. Unfortunately, even with a seating plan, there will be some cases where you will be sitting adjacent to each other because the IT is not very big. The size is 150 and we have a car size of 90 plus. So there is no way we can avoid some people sitting next to each other. So I leave it to you and to your integrity to make sure that you don't look at your neighbor and answer. But I should not see you being separated by more than 2 seats. And that is, there should be at most 1 seat in the middle. Okay, if there are 2 seats in the middle, that calls for a reconfiguration, so I will have to ask somebody to move and sit. Okay, so yeah, that's the seating arrangement. So yeah, please make sure that you are back in your seats by 7:15.
Recording stopped.
Holy shit, what a day.
Slides. The 3 inputs needed for logic synthesis are HDL code, constraints, and technology library. Okay? The whole process of synthesis is putting together components from the technology library to achieve the functionality as described by HDL code, while obeying the constraints or respecting the constraints that are given as No. Even at the stage of logic synthesis,
Okay, I got one more.
the technology process is technology dependent.
But later he tell you not state machine, huh? Then everyone just wants to
Even for FPGA, logic
There goes
synthesis,
zero.
transit to technology dependent components available.
So don't choose anything other than branch. One down.
Which of the following statements about a single circuit
Everything.
processor is true? Well, for any circuit that has at least one flip-flop, it's a state machine. Processor is of course one of the most complicated state machines that mankind has ever designed. Right? The number of states is quite huge. Every bit of storage gives it two states. And there are so many bits of storage in the processor. Processor register, program counter, processor flags. Even memories are considered storage elements, and every possible combination is essentially a storage state. And through the course of instruction execution, that is, at every clock edge, something gets changed, and that is essentially a change in state. Yeah? So it is a state machine, no strings attached. And here it's technology. Now question number 3. Memory control signal can be asserted without causing functionality issues for the following instructions. In other words, which are the instructions for which it's okay to assert memory right? Obviously, load, because if you look at this,
Obviously.
the question asks, what are the situations or what are the instructions for which the data is supposed to flow this way? Or it's okay for the data to flow this way, right? That is obviously for load. How about any other instructions? Store. Why store? For store, it's perfectly okay for the data to flow this way because this data is eventually not used anywhere else. So for store instruction, when to write is actually don't care, which means it's okay for it to be known. Now this is for ARM. For RISC-V, if you chose RISC-V, there is one more branch. Because in RISC-V, branch is not computed in the ALU. It is computed separately using a separate circuit. Okay, so nothing from the memory, nothing from the ALU goes into a register for branch in RISC-V. So if you chose RISC-V, branch is also one of the answers. But most of you would be following ARM version 3, for which these two are the correct answers. So if you chose only one of them and not the other, you will get partial marks. But if you chose at least one wrongly, you get 0 marks. So if there is any answer where branch or data processing are chosen, it's very wrong, so you get 0. But if you chose only load and not store, you will get half the mark. Yeah? Now question number 4, which I am sure most of you got wrong. Okay, instruction memory 300 picojoules, register is 1000, this is per port. So if there are two registers that are read, it's around 200. Yeah, per port, per read port. ALU 200. Data memory 300, register file write 100. So assume that we are looking at a load instruction. A load instruction does all of these, or does it? What is the energy requirement for load instruction? Okay, it reads instruction memory for sure. Every instruction does. Register file read. A load instruction doesn't read one register or two registers. It reads only one register, but in reality, or to be precise, you read both registers, but you read one. The other register is also actually read. There is still some binary value that is going into RI2 here. There is something going in for sure. So there is something coming out for sure. It's just that you don't use it. Because for a load instruction, the second operand to the ALU comes from immediately. Which doesn't mean there is no energy incurred in reading a second register. It's just wasted energy because you are raising it, you are not using it. Yeah? Any operation, yes. Data memory, read or write, yes. Because it writes, sorry, it reads. Register, write, yes. So the total amount of energy consumed for load instruction is 1100. Some of all of this. Now how about for data processing instructions? Data processing instructions have nothing to do with memory, right? So is energy incurred? The answer is yes. Why?
Yes.
Was there any way to block the data memory from reading something? You are still giving something to data memory. It's actually an invalid address. You are getting some invalid output. You are not using it because the output that you are using is from A. So the energy is still incurred. Unless you had some mechanism whereby you disable the memory for data processing, which you didn't do. Right? So can I say that for all instructions it's going to be 1100?
Can we reverse simulation?
Not really.
No, it's not
There are
correct.
two instructions which are exceptions. Which are the two? Store and branch. Store and branch do not write to the register file. So the energy incurred for writing into register file is not to be counted. See, it's clearly mentioned here. When they are enabled or activated. So register file is explicitly not activated for branch and store. So for branch and store, it's going to be 1000, not 1100. For all other instructions, it's 1100. So it is simply 1100 into 0.6 plus 1000 into 0.4. Okay, you don't really need a calculator to do it. It's 1060 picojoule. Okay, 10 raised to 9 times a second. Okay, so that is essentially 1.06 into 10 raised to 12 picojoules. So into 10 raised to minus 12 joules, which is 1.06 watts.
And also 1 watt. Like, you know, I didn't get 1 watt because of that place.
So the important takeaway here, no, I did not have this question just to make fun of you. It's to bring in this important point that you should not assume that simply because you do not use the data of a certain unit means the unit consumes more power. Okay, if you don't want a certain unit to be activated for a particular instruction and to save power in the process, you have to have some sort of enable mechanism for that unit. Okay, which is enabled only when it is relevant. Yeah. Yeah, so here also there is something going into array for sure. Well, the question says that it is incurred as long as you don't disable it. So the idea is that even if it's the same thing, it will still, okay, you do have a point that a lot of transistors don't really flip. But if you go by the question, it says that if it is not enabled, it's incurred. Yeah, in reality, yeah, if things don't really flip or change, it doesn't consume power. So for example, if RI2 from the previous instruction is exactly the same as the next instruction, then there is no real change or flipping of outputs of transistors or gates, and then of course there is no energy.
Oh my god.
Okay, but in general, you know, it's very unlikely that you will have the same RI2. And that's why in modern processor design, those components and parts which are not used are explicitly
So
disabled.
now you can get 2 points
Because every
instead of
picojoule of power matters.
instead of 1.
Because eventually when you are looking at billions of instructions, it adds up. Okay, and it can cause a few hours of difference in battery life if you disable units which are not used in that particular circuit. Yep. Now the last question, which shouldn't be that hard. You are looking at a benchmarking scheme which is very similar to spec in 2006, where the execution times of the machine under test and the reference machine are given. How do you compute the benchmark score? You have to find the execution ratios of each program, execution time ratio. So the first program runs on the machine under test in 10 nanoseconds, whereas the reference machine takes 40 nanoseconds. Which means for the first program, our machine under test is 4x faster. Yep. And for the second program, the machine under test takes only 12, whereas the reference machine takes 60. Which means the machine under test is 5x faster. And for the third program too, it's 5x faster. So the execution ratios are 4, 5, 5. So how do you compute the benchmark score? Cube root of the product. It's essentially geometric mean. Okay, which is cube root of 100, and that's it. If you just give it as cube root of 100, okay.
What the fuck is cube root?
You don't have to compute it as I did as I Now again, that's why I have this question. Do you think this sort of a benchmark game is okay? There are a bunch of issues with this particular benchmark. What are those? Any guesses? Yeah. Number one, you can see we are counting in nanoseconds. To make any statistical sense, it has to be at least a good part of a second or seconds. Okay, how much of performance evaluation can you do in nanoseconds? You are looking at a very few number of instructions per program, which is probably not very representative of anything in reality. So, too short a program would not allow you to measure anything. You can't even measure time with that kind of a precision. So that's number one. Any other issues? Second, using only 3 programs is certainly not going to be enough because benchmarks are supposed to be indicating what real-life workload. And if you are evaluating a real-life workload or a real-life situation using just 2 programs, it's certainly inadequate. You have a variety of programs which people are likely to run with a variety of requirements and type of computation. Yeah. And there is a third issue, which I am not saying is certainly an issue, but a potential issue. To make matters worse, it looks like all the 3 programs are somewhat similar. Because you see, the execution ratios are very close to each other.
You know the question one, right?
Which again is probably not very
This slide of 2A, but that's the only question I can answer, I think.
which a benchmark
Technology library.
is supposed to do.
The 2A, chapter 2A. Slide 12, I think.
So if you look at the real spec in 2006, you can see it uses a large number of programs. Different programs with vastly different execution ratios. And each program takes a really long time, several seconds to do. Okay, so that's it, folks. Now we will continue with what we were discussing, which is floating point. If you have anything urgent to do, you can leave, but the lecture is not over. Well, if you want to get the most out of it, please do stay with us. Okay, so that completes that. Now, let me go back. Floating point numbers. I didn't know I have this effect that people don't better than that. Okay. Floating point, as the name implies, is a representation where your point can float around. Unlike in fixed point system where the position of the point was fixed and implicit and agreed upon beforehand by the various systems that it trust. Okay, the various systems that pass information with each other or from one to another. So it floats around. And how do you allow point to float around? The idea is that you use scientific notation. So if you have a number 1073 in decimal, how do you write it in scientific notation in decimal? I'm sure you had done it in secondary school sometime, right? So you would write 1.073 into 10 raised to 3. This is what we call scientific notation. Yeah? And that is the starting point, or that is in fact the notation used by floating point format. So a number is written as 1 point some fraction bits into 2 raised to exponent minus 127. So a number is converted into this format, and once a number is written in this format, you can take out the fraction part and the exponent part, and of course you know the sign, and that's how you package a floating point number. Okay, will be a lot clearer when we look at this example. Represent a minus 58.25 decimal in floating point. By the way, when we say floating point, there are a lot of different variants, but unless otherwise stated, we are looking at what programming languages refer to as float, which is 32-bit floating point. So when you write float, it doesn't depend on the word size of the processor. The compiler treats it that you are looking at 32-bit floating point format. So let's first write it in binary. Okay, don't worry about the sign for now, because in floating point format, sign is encoded completely separately. Okay, so sign is already taken care of, and in this case, sign is 1 because the number is negative. Now 58.25. Okay, when you have nothing better to do, you can do the conversion, and by this time you should be quite comfortable with that. It's nothing but 64 minus 6, which is 63 minus 5, and 63 is 6 ones minus 101, which is 111010. Okay, so that's 58. 0.25 is 1 by 4, which is 1 by 2 raised to 2, which is 0, 1. There is no 2 raised to minus 1, so it's so 0 into 2 raised to minus 1 plus 1 into 2 raised to minus 2. And here we are looking at 2 raised to minus 2 itself, so it's 0, 1. Yeah? Now, in scientific notation, you write it as 1.111. So you can see if you move the point here, you have 5 digits after that, 5 decimal digits or bits after, 5 binary digits or bits after that. So you write it as 1.11 whatever into 2 raised to 5. Now we package it. So you see the format is 1 point fractional part, and this is the fractional part, and that fractional part is packaged here. It's the same thing. Yeah? And this fractional part can be up to 23 bits. So in this case, there are a lot of zeros after that, and that's why you have a lot of zeros after that. So this digit is the one which is the immediate right to the point. Okay, and so on. And this 5 is not written as 5. Exponent minus 127 is equal to 5. It's into 2 raised to 5. So exponent minus 127 is equal to 5, which means exponent is 127 plus 5, which is 132. So this is 132, which again is easy to see. 1 followed by 7 zeros is 128, plus 4 is 132. Okay, plus 1 0 0. Yeah? So yeah, this is the 32-bit number that you see in memory when you write, say, float A is equal to minus 58.25. So when you inspect that memory location, when you run your program, this is what you will see in that memory location. Yeah. So next time give it a try. Take any compiler which has a decent debugger which allows you to inspect memory, etc. Okay. Figure out what is the memory address corresponding to float, which can be easily done by, taking a pointer to that and printing out the pointer value. and then go to that memory location and see what is in there. Yeah, and you will see it is this. You can also directly print it with some gimmicks. Give it a try. Like you can take a float, then read the address or get the address using a floating point pointer, then cast it to an integer, and then print out the value. And then you will be able to see the actual binary pattern or integer corresponding integer, which can be in hexadecimal. So what I meant is something like this. So float star b is equal to address of A, and then you do something like say int star, let's say ptr is equal to int star b. You are essentially casting it to an integer, and then do something like say printf percentage x star b. Okay, so if you do something like this, you can actually see the integer value or the hexadecimal value, which should look like this. Okay, give it a try. It takes only a few seconds for you to do that. So anyway, this is how floating point format is, and this is how it will appear in the memory if you are trying to represent this. Now, the one to the left of the point was not accommodated anywhere. Why did we not do that? See, this part went in as so-called fraction field, which is 23 bits out of 32, by the way. This is 8 bits. This is 1 bit. So what happened to that 1? That's what we call the hidden bit. It's implicit. You don't have to waste 1 bit representing it explicitly. Because in binary, the moment you express something in standard, scientific notation, is going to be 1 point something into 2 raised to something, right? Unlike in decimal, there is no alternate possibility here. It has to be 1 or 0. If it is 0, it's no longer in scientific format. So it has to be 1, right? So yeah, you have 1 there. So 127 here is what we call bias, because it can be positive or negative, the overall value here. The overall value here. For example, if you are trying to represent 0.0010, it will be written as 1.00 into 2 raised to minus 3. Basically, you move the point right by 3 positions to make it scientific, and to compensate for it, you have to have 2 raised to minus 3, so that the overall value doesn't change. So this can be positive or negative, but what we do is add 127 to it, and then represent it here. So that will make sure that that value is always positive. Okay, the max you can have is up to minus 127. So if you add 127 to it, it becomes 0. So nothing goes negative or becomes negative here. Yes. So you are adding a bias of 127. So if your original number is 1.0 that you are trying to represent, it's 1.0 into 2 raised to 0. And this 0 is represented as 127 here. Anything negative will be, or a number less than 1 will be less than 127 here in the exponent. That's right. Now, 1 point something, this part overall is called significant. Okay, 1 point some fraction part, right? This overall part is called significant. I forgot to mention this in the notes. Again, I will add a correction later. But having said that, this terminology is not so standard. Okay, it's a bit more standard than what it was for fixed point, but still, if you look at different textbooks or if you ask different people, they use different terminologies for all these. Okay, but the IEEE recommended terminology is to call this whole part significant. Okay, but in Wikipedia, it is written as 1 point fraction. So I am just following what is in the Wikipedia. Okay? But different textbooks have different terminologies. Some people also call it marquesa. Okay, but the term mantissa as well as fraction have ambiguities because they are used in different ways in different contexts in mathematics, which does not entirely match what we are looking at here. Okay, so the most unambiguous term to be used is significant. But there is an ambiguity, unfortunately, on whether the hidden bit is included or not. So 1 point something, right? So whether that 1 to the left of the point is included in the significant or not is again context dependent. Yeah, unfortunately that's what that is. Yeah. So if you look at a lot of textbooks, they use the term mantissa, but some of the pioneers in computer science like Donald Knuth recommends that we use the term significant because those are the significant digits. Yeah. Now this floating point representation is, unlike fixed point, not a linear representation. In the sense, the overall binary pattern does not linearly vary with the quantity. Because here you can see it is composed of multiple fields, which wasn't there for fixed point. If at all there were multiple fields, it's only the part before the fraction and after the fraction. Okay, which still varies, the representation still varies linearly with the value represented, which is not the case here. So floating point is what we call a log linear representation. There is some linear part, which is a significant, and there is some logarithmic part which is an exponent. Yeah? So that makes it a bit hard to answer questions like, is floating point better than fixed point or not with respect to precision, with respect to range? Okay, all these are difficult questions to answer because you are comparing two totally different representations. You are comparing apples and oranges. Yeah? And as is usually the case in real life, it is impossible to categorically state one is better than the other without knowing what is the context and what is the application. If one is categorically better, the other one wouldn't even exist, right? Now, there are some problematic cases in floating point. How do you represent a real zero? Because a representation is 1 point something into 2 raised to something, right? No matter what you put here, it's never going to be really zero. That's a problem, right? And that's one of the problems with floating point. So 0 has a standard representation where the significant bits are all zeros. The exponent field is also 0. Sign is immaterial. Okay, in reality, if you follow the same representation system, it's plus or minus 1.0000 into 2 raised to minus 127. Which is a very, very small value because 2 raised to minus 127 is 1 by 2 raised to 127 into 1, okay, which is approximated to 0. Okay, but it's not just based on the approximation. The IEEE floating point standard specifies that a 0 has to be represented this way because there are a lot of scenarios in which you can't, it's not good enough to approximate 0, you want an exact 0. Yeah? Then there are other numbers like minus infinity and plus infinity, which is exponent of 255. Exponent field being 255 means it's into 2 raised to 128. 128 plus, yeah, 128 plus 127 is 255. Right? So 1 point something something into 2 raised to 128 represents plus infinity, whereas minus 1.000 into 2 raised to 128 represents minus infinity. Okay, again these are in some sense sensible that it's close to this is actually very, very high, this is actually very, very low, so it's treated as plus and minus infinity. And then we have exponent being 255, significant being non-zero. So a very high exponent, but significant is non-zero. And this is not a number, NaN. Okay, you must have seen some poorly designed applications and websites where you enter a certain value, and then it gives you an output NAN. Okay, that's because internally they are using floating point, and they haven't really tested those cases that you entered. And it causes possibly something like a division by 0. So if you do a division by 0 in a floating point hardware, the result that you get is NAN. Because division by 0 doesn't give you anything meaningful, right? Now, there are double precision representation formats. There is also half precision. The one we have seen is 32-bit precision. There is double precision, which is the default data type in some of those languages used for scientific computing, where you have one sign bit, 11 exponent bits, 52 fraction bits, and bias of 1023. This bias is of course closely related to the exponent field. The bias is always 2 raised to exponent minus 1. So 2 raised to 11 minus 1, sorry. Bias is always 2 raised to exponent minus 1 minus 1. So here exponent is 11, so exponent minus 1, exponent bits, not exponent. So the number of exponent bits minus 1 is 10, so 2 raised to 10 is 1024 minus 1. Okay, which kind of makes sense because bias is something which pushes the exponent to halfway when the exponent is in fact supposed to be 0. Yeah? So that negatives can fall on the lower side, positives can fall on the higher side. 0 will be in the middle. Yeah? And that's why you require, or you are looking at 10 exponent bits. So 2 raised to 10 minus 1 in this case. So the bias is 1023. Fraction bits is 52. So earlier what were the numbers? Earlier, of course, one sign bit is one sign bit, can't be helped. Here it was 8 and here it was 23. So when going from 32 bits to 64 bits, they didn't really double the exponent bits. They increased it only by a bit. Whereas this was increased tremendously. So things are not progressing according to scale, right? Why so? Any idea? Remember, even using 8 bits, you could go all the way to 2 raised to 127, which is already a huge number. Okay, and by increasing 3 bits, you are able to go to 2 raised to 1023, which is unimaginably huge, which is much more than the number of atoms in the observable universe, if I'm not wrong. So yeah, you don't have to throw in a lot of bits, because this part is the exponent, right? So that should already tell you that adding 1 bit there increases the number of possibilities quite a lot, increases the range of representation quite a lot. Now half precision is 16-bit precision or 16-bit representation of floating point. One sign bit, as is always the case, 5 exponent bits, so that 8 came down to 5 and that 23 came down to 10. Here again, the exponents were not drastically reduced because drastic reduction in exponents will limit the range of numbers that you can represent, the maximum number that you can represent. And here the bias is 15, which makes sense because 5 exponent bits, 2 raised to 4 minus 1, which is 16 minus 1. It's becoming very, very popular these days. Lot of hardware manufacturers are adding support for lower number of bits of precision, which sounds like a bit of a regression, right? And instead of going towards higher precision, we are going away from higher precision. Why so? I probably gave the answer sometime earlier, but anyone has any guess why we are going backwards rather than forwards? Yeah, the answer is we don't need it in many cases. These days, a lot of computations are related to machine learning. And machine learning is one application which is highly tolerant of low precision. Right? So if you can reduce the precision while compromising a bit on accuracy, you're okay. Like for example, you are using a face unlock application. Okay, if it unlocks correctly, let's say 90 out of 100 times or 95 out of 100 times, you are pretty happy. But going from that 95% of accuracy to 98% might require a lot more bits, which naturally translate to a lot more computation, a lot more storage, etc. Probably not worth it. Okay, I am happy to show my face battery extra time out of 100 times if my battery life can be extended by an hour or two, right? So that's the idea. So that's why a lot of hardware these days are adding support for lower bit precision. Example would be, NVIDIA's GPUs, Pascal series or newer, and newer CPUs as well. Like for example, ARM version 8.1M. 8M did not have. 8.1M has half precision instructions, where you can deal with things at half precision. And 8086 x86 has this AVX512 series instructions, which also support half precision. But if I'm not wrong, there is no processor with this yet, or it's supported only in the most recent series of Intel processors. Okay, 2 years ago it certainly wasn't. So yeah, now let's look at the issues or how to deal with some of those issues. Underflow and overflow are a problem with all possible representation systems, and floating point is no immune to that. Overflow means that you are getting a number whose magnitude is too big to fit into the given number of bits. Like for example, using standard integer representation, if you are trying to represent 2 raised to 32 plus 2, yeah, you are out of luck, because the max you can do is 2 raised to 32 minus 1, unsigned. Anything more, and you have a problem. And that problem is what we call carry, but I was following ARM terminology. But if you look around, a lot of people say it's overflow. Okay, because in a mathematical sense, it's overflow, but ARM distinguishes clearly between overflow in signed and overflow in unsigned. And overflow in unsigned, according to ARM, is simply called carry. Okay, so I was making that distinction by following ARM terminology. Not everyone follows the same terminology. A lot of people say or would say that 2 raised to 32 plus 2, or if I am doing, let's say, 2 raised to 32 minus 2 plus 3 will result in an overflow. But in reality, according to ARM, it's carry. But from a mathematical sense, what you are getting is overflow. What you are having is a number which doesn't fit into the representation system or the given number of bits. Now, underflow can happen. If you are doing, let's say, 23 divided by 2 in C language, where 23 is int, so int A is equal to 23, int B is equal to 2. Int C is equal to A by B. What will you get? Is it 11.5? No, it will just give you 11. What's happening there? Underflow. Because the representation system that you are using, which is integer representation, cannot represent anything which is smaller than 1. Right? The smallest possible value that can be discriminated in that number system is 1. Anything below 1 can't be represented. That's right. So that's called underflow. The given number of bits is simply not enough to represent the result precisely. That variation in the result or the result itself is too small. Okay? Which will be even more apparent if you do 1 by 2. The result becomes 0, because the result, which is supposed to be 0.5, is too small to be represented using integers. Now, whenever you have this kind of an issue, well, you have to deal with it. Overflow has no standard way to deal with it. There is hardly anything to talk about. It's entirely your problem, right? If it doesn't fit, find some other way to make it fit. Otherwise, throw up an error, right? Like for example, YouTube had this view counter, and which is the first video to cause some issue with the view counter? Anyone?
Gangnam Style.
Sorry, I'm not a dancer, so I can't imitate, but Gangnam Style, right? It is the first video that hit 2 billion. Okay, they used a 31-bit representation to count the number of views, but they had enough intelligence at least to detect that it crossed that point and saturate it there. So one way to deal with overflow is to saturate. Don't allow it to count or continue beyond the max. If the result is beyond the max that you can represent, clip it to the max. Yeah, and that's called saturation. So YouTube actually used a saturating counter. Okay, it counts until a certain point and doesn't go beyond that. Okay, but other than that, there aren't so many ways. But you could always come up with your own custom representation system. Like for example, if you are using an object-oriented programming language like C++, you can always define a custom class which can deal with a bigger size of data, and then use smaller operations while mimicking a larger object, an object which has a larger number of bits. So these are all possible ways you can deal with large numbers. How about small numbers? That's when you do some kind of rounding. Rounding, it can be rounding down, rounding up. Even for large numbers, you can of course do rounding. Saturation is a form of rounding. Okay, you are rounding it to the highest possible number that can be represented. So down, up, towards 0 and towards nearest. Let's see with examples. So you are looking at 1.10101 and you are using a representation system. Whatever it is, it doesn't matter, but we can have only 3 fraction bits. And typically if you have 3 fraction bits, okay, it's either a floating point representation with a 3-bit so-called fraction part or a fixed point representation. Rounding down, that the nearest possible representable value which is lower than the one we are trying to represent, which is 1.100. Rounding up, well, needless to say, the nearest next higher value that can be represented precisely. Rounding towards 0, rounding towards 0 is rounding down for a positive number, rounding up for a negative number. So let's say if these are the possible representable levels and this is 0. Yeah. Now we are trying to represent a number here. If you are rounding towards 0, you will take the representation of this. How about if the number you are trying to represent is here? If you are rounding down, you would have taken the representation here. But if you are rounding towards 0, you will take this representation. So for positive numbers, you round down. For negative numbers, you round up. Which is actually the easiest thing to do. Because all you need to do is just cut off these bits. Cutting off those bits doesn't mean rounding down. That's a popular misconception. Because if the number is negative, you are not rounding down, you are actually rounding up by cutting off those bits. Because the representation that you end up using is higher than the number you are trying to represent. Yeah? And there is a nicer name for this, which is what C compiler does, by the way. If you try to represent a number which is actually a number with fractions in integers, it will just cut off the fractional part. So even if you write something like, say, float A is equal to 1.99, then int B is equal to A, B will contain 1, not 2. So this is what we call, anyone? Truncation. You just truncate or knock off all the bits that you can't accommodate, which is in most cases the easiest thing to do. Then there is round to nearest, which is computationally a bit harder. You have to look at which one is nearest. This is typically what humans do in real life, especially for economic or commercial transactions, right? You'll just round to the nearest digit. So let's say a shop has no balance to give you, and if you are paying in cash, if the item costs $1.90, they will just take $2 from you and won't give anything back, right? Whereas if it is 1.1, if the shopkeeper is nice enough, he will say, okay, 1 is enough, right? Yeah. So that's rounding to nearest. So here, 1.100 is 1.578125. 1.10, sorry. 1.100 is 1.5 decimal, whereas 1.101 is 1.625. And we are trying to represent 1.578125, which is nearer to 1.625 than to 1.5. So it will take the representation of 1.65. And this error that you incur because you are forced to knock off certain bits is what we call a, anyone? Yeah, a bit more precise, well, you can say rounding error, but a bit more precise term to use is quantization error. Because using a certain representation system, you can only represent certain quantum. So here, all these steps that I was talking about are certain quanta. And your representation or the eventual representation has to be one of the certain quanta. Okay, so here, the difference between the number you are trying to represent and the number whose representation you eventually end up taking is your quantization error. Okay, and for usual representations, it drops exponentially with the number of bits. Okay, there is a mathematical proof for that. Okay, it's commonsensical, but yeah, there is a nice proof because it's important in communication systems where you add in or throw in more bits and your signal to noise ratio increases exponentially. And that's the whole motivation for using digital systems where the only noise ideally encountered is quantization noise. Okay, because the way digital systems are designed are such that all other noises can be sort of eliminated. Unlike analog systems where every time you amplify the signal and noise. And to make it worse, the amplifier itself introduces noise. Whereas in digital systems, every time you receive a digital signal, it undergoes a cleanup rather than further corruption. Okay, and that's why analog systems are entirely replaced with digital systems these days, right? Increasingly. Like I think Singapore has already turned off analog TV transmission. It was there until I think a couple of years ago. So anyway, yeah, that's just relating into some other real life scenarios. Yeah. Now let's say we want to do an addition of two floating point numbers. How do you go about doing that? For fixed point, we saw it's super easy, right? We can just add it like how integers are added. Okay, which means one order or one step operation. Whereas for floating point, things are a bit more complicated. Why? Well, because the format itself is more complicated. So once you get a number, you have to unpack it, extract out the various fields, do the operation, adjust the various fields if need be, and then pack it back. So there is a bit of a process involved, which will be clearer if you look at these examples. We have, let's say, these two floating point numbers. This is how they appear in memory. Now we have to unpack and see what they really represent or what it really means. So you have one bit, the first bit which is sign, so it's positive. Then we have 8 bits which are exponents. And one problem with this representation system is that all these boundaries don't even align with byte boundaries, okay, which makes operations rather inefficient. But yeah, that's what that is. So here you can see these will be one part of one byte, and this will be a part of the next byte. But no choice but to extract out all the bits, so that you can make sense of all the bytes, so that you can extract out the exponent field. And then the fraction field. And here you can see the exponent field is 127, which means that the number we are looking at is something like 1 point something into 2 raised to 0. Because remember it's in XS 127 format, right? So 1 point something into 2 raised to 0, and what is that something? Here. So it's 1.1 into 2 raised to 0. And here it is something into 2 raised to 1 because it's 128 here, 1 followed by 7 zeros. And it's 127 plus 1, which means it's 2 raised to 1. Okay, so it's 1.101 into 2 raised to 1. This is the other number. But this is for humans. Of course, computers don't really convert it back into this straight away. So let's see. The first thing that we need to do is to add the hidden bit. This hidden bit is not there anywhere in the representation. It's hidden, right? But for mathematical operations, we can't really allow it to remain hidden. We have to insert that hidden bit. Then you get these two significance like this. Remember, significant is 1 point, whatever is a fraction bits. So you have these significant bits, and then you compare the exponents. So if this is number A, this is number B, what you do is exponent of A minus exponent of B. And here it is 127 minus 128, which is minus 1. Okay, which simply means that the first number is smaller than the second number. Yeah? So you shift the smaller number or the significant of the smaller number right by 1 position. And here n1 or the first number A is shifted right by 1 position. If this was positive, you shift the second number right by 1 position, because the second number is smaller. So basically shift the smaller number. So here the smaller number, which is 1.1 into 2 raised to 0, is shifted right. So that becomes 0.11. But then there is implicitly into 2 raised to 1, because if you move the point to the left, you are in fact dividing it by 2. So you have to keep in mind that there is a into 2 somewhere, it has to be. And for now, we keep it in our mind. Yeah? I mean, it's just the implicit part that arises out of this. And the result of this is that now the positions or the points are aligned. Earlier the points were floating around, so the two of them had actually different point positions. Yeah? So you are aligning them. So in other words, this was the first number was 1.1, the other one was actually 11.01. So you are aligning the two this way. So this is shifted right, so that it becomes 0.11, and implicitly, so then, okay, so here it is 0.11 into 2 raised to 1, and this 2 raised to 1 was there for this, right? For the bigger number. So you are essentially aligning the smaller number in such a way that the point corresponds to that of the bigger number, so that the exponent fields are now the same. So earlier it was 1.1 into 2 raised to 0, so you wrote it as 0.11 into 2 raised to 1. Now it is okay to add these two together, because now the points are aligned. Earlier it would have been quite messy, right? it was something like 1.1 into 2 raised to 0. The other one was 101 into 2 raised to 1. So you can't really do anything with these two directly. So you have to align them in such a way that the points align, and then do the operation. Okay, just like how you do integer operations. Okay, you can even assume that this part is now an integer operation. The hardware is exactly the same, because once the points are aligned, you don't have to worry about where the point is anymore. And then you get 10.011, and that gives us a bit of a headache, which is this is no longer in scientific notation. So you have to adjust the position of the point to make it in scientific notation. So the result is now adjusted, and that adjustment in point, which is the point being moved to the left, has to be compensated by an increase in exponent. Now you have it in scientific notation. Now you can do packing, and if this bit or this field has more than 23 bits, you have to do rounding. Some kind of rounding depending on the rounding mode that is used. But here, luckily enough, it's far less than 23 bits, so there is no rounding required. Okay, so pack it back. So now your exponent field will be 127 plus 2. Sign didn't change at all, 0. And this part, 0, 1, 1, is your fractional part. That's ideal. So now you see the problem with floating point. Even to do a simple addition, there were a lot of steps. So you have to unpack it, by adding the 1 to make it the significant. Then you have to align them by comparing the exponents. Then you do operation, and then you have to do normalization or rounding, etc. Normalization is normalizing to standard scientific notation, which is basically 1 point something. You have to do rounding if necessary, and then you have to pack it back. So a lot of different steps are involved, and that's why floating point operations are almost never done in simple cycles. Okay, not even addition. So that's a problem. And that's why if you don't really need floating point, like in many applications, using floating point will be like using a cannon to shoot an ant. Okay, you don't really need that kind of flexibility that floating point offers. I mean, floating point can represent a really wide range of numbers, like 0.0001 to 1 into 2 raised to 126, etc. Right? Without any change in format. So that's a beauty. But that comes at a price, which is a lot of additional computational complexity involved. So yeah, that's why fixed point is also quite popular, especially when dealing with numbers which do not fall in a very high range. If the dynamic range you are looking at is rather limited, in many cases you can do the same thing with fixed point with far less power and computation requirements. Yeah. Now, interestingly, in a lot of machine learning applications, it's not unpopular to totally ignore this part. Sometimes just the exponent field will do. Okay, that precision, extra precision offered by the fractional part is probably not too important. And that kind of quantization is called logarithmic quantization. Yeah? And these are all very popular, not very popular, very promising techniques that people are using to make machine learning computations a lot faster. Okay, and if you can reduce the number of bits, etc., you can reduce the storage requirements, you can reduce the amount of data transmitted, that's the bandwidth requirement. You can also reduce the amount of hardware required and power required. Okay, and many times the hardware requirement is not linear with the number of bits, it's more than linear. And in some really bad cases, it could even be exponential. Okay, so by knocking off bits when it is not necessary, you could end up saving quite a lot. Okay, and these are all relatively hot research topics. If you are interested, you can read up more about it. Yeah. Now, floating point versus fixed point. Again, just a couple of examples. So if you do something like, say, 2 raised to 32 minus 2 plus 3. Try doing this in both fixed point and floating point. Or fixed point means integer. Okay, integer is just one special case of fixed point, in fact. Okay, where the point is fixed right at where you naturally expect it to be. Yeah. Fixed point is a more generic format where the point can be anywhere. Can you represent 2 raised to 35 using fixed point? Yes. Just that the point will be, instead of going to the left, it will be going to the right. That's all. Yeah. So as long as you use appropriate representation system, you can represent bigger numbers too, even using fixed point, even using less number of bits. But of course, there is a price to pay, and that's precision, right? So this precision versus range trade-off is something which you will come across in a lot of computation scenarios. Okay, for a given number of bits, either you can have a wider range or higher precision. Especially when you deal with sensors, etc., it manifests all the time. IoT systems, okay, you will have it all the time. Now coming back to this question, 2 raised to 32 minus 2 plus 3. Try using normal integer representation and sign. Sign can't go to 2 raised to 32 minus 3 anyway. And using floating point. Okay, see what you observe. Write a small program. It's no big deal to do this. And print your result. The results are interesting. You will see that floating point will still give you a result which looks mostly correct. Whereas integer results will be radically wrong. Why is it so? Okay, it's easy to see why integer results would be wrong, right? Because the max we can go is 2 raised to 32 minus 1. Anything more, it will sort of wrap around and give you a carry, and your result will be very close to 0. In this case, it will be 1. Your result will be 1. Drastically, radically wrong. Because there is, well, mathematically there is overflow, and in ARM terminology there is actually a carry. What if you do this same thing in floating point? You will see that your results are not that radically wrong, but slightly wrong. Why is it slightly wrong? Because 2 raised to 32 plus 1, which is supposed to be the result, cannot be represented precisely in floating point. But it doesn't give you a radically different result because 2 raised to 32 can be represented. 2 raised to 32 is 1 into 2 raised to 32, which is 1.000 into 2 raised to 32, which will mean that the fraction bits will be all 0, exponent field will be 127 plus 23. Sorry, where did that 23 come from? Sorry, 32. Yeah. Okay, you are looking at 2 raised to 32, right? Sorry. Yeah. So yeah, this number can be precisely represented. How about this? In scientific notation, it will look like 0, 0, 0, 0. You will have 31 zeros followed by a 1. Okay, into 2 raised to 32. And only 23 bits from here will be accommodated in the eventual representation. So the last few bits will be knocked off. So 2 raised to 32 plus 1 will take the representation of 2 raised to 32. So your result is wrong still, but it's not catastrophically wrong like how it was for fixed point or integers. Yeah? And that's generally the case. Floating point tends to give you a bit more graceful degradation in correctness. But again, all these statements are something which we need to make very carefully because everything has some context dependence. But yeah, hope you got some idea about all these number systems, etc., which are all very important, not just for computer architecture or this module. Whenever you deal with any real life computations, knowledge of all this can be very useful. Okay? It probably doesn't matter if you don't care about efficiency, but in real life, many times we will care about efficiency, right? And then all these are very, very important. Okay, so yeah, that's all. Let's see in a couple of weeks, right? Because next week is Christmas week, and I will look at the chapter on pipelining from week 7 onwards. The first around 20 slides will be somewhat familiar to people who have taken CG3207, but the second half is something quite different, quite involved, not a walk in the park, but a lot of fun as well.
Record